Wednesday before Thanksgiving break. He said it. What is the date?
The 20th.
That's the 20th.
November 20th, and that's Wednesday.
No.
20th, so Friday
We have a thorough 3110 exam on that day.
November 22nd, right? Monday would be November 18th.
No,
No,
not
not
the
Monday.
I'm just putting it there for context. What other dates? I know you said the 20th. Any other dates?
18th. That's, yeah.
Yeah, that's good.
I'm trying to get a feel for it. Are you okay voting in this week, guys? This is the week before Thanksgiving break, okay?
Yeah.
All right, now, one.
This is the week you're going to go to the Georgia game, right?
No, this is a week before
After
the Alabama. Oh wait, no, before the Stanford game.
It's after Georgia. All right? So, I mean, it makes sense. You want it probably about that week. That makes absolute sense. So, let's do this. Make sure everybody's together on this. I need somebody else to count with me. Laughing about you. How about both of you? All right, count with me on this one. If you want to just, work with me. You know my thoughts. Monday's a great day, but if it's the Georgia game, I mean, you're going to be unable. Normally, Monday tests have the highest average, with the exception of when there's a circus on campus. And then Wednesdays, and Friday's usually the worst, but I don't know. It all depends, I guess, sometimes on what's going on the weekends. Here, what I'm going to do is ask for a show of hands. We'll run off the top two. If you want it Monday, November 18th, one hand, and one hand only. Hold them up high, and I'm going to tell you. I got 1, 2, 3, 4. You count 4? 4? You got 5. Who else? Put them up again. 1. Oh, I said 2.
I'm taking back my vote.
Really? No, just 4. Oh.
If you want it Wednesday, one hand. And hold them up. And don't put them up.
Well, I don't.
Just for a record. 2, 4, 6. Count with me. 8, 10, 12. Is that up or not? 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 39, 40. I got 40.
So how many people in this class?
I got 30.
I got 46. This person doing this. I think it's over, but if you want Friday, one vote just for the record. All right, 1, 2, 2, 4, 6. I'm counting 6 hands.
You got an arrow. You
Hey,
I want that free day.
We'll run it off again. I'm just going to do this. If you want it Wednesday, one more time, one hand. One hand. All right, Friday. 2, 4. Just, okay. Wednesday.
I was gonna say there's a 10 times
If
deficit.
you do me a favor, can you send me an email saying 3810 test Wednesday, November 20th? Yeah, do you have a question?
Also in regards to last test, when you were talking about before, like the final scale on it and stuff, was the one version that got scaled up like 10 points out of the 40 compared to the other one? Like I was just trying to,
Yeah.
read it. So the other one didn't get scaled at all?
That's right, because it honestly, to be frank about it, that average, the two averages are almost the same after the scale. All right, so what I did, what we scaled, and the real problem is people don't know how to use their calculators, and that was the real reason. So one problem got thrown out. They were messing up because they had a real and an imaginary number that they had to divide by. They didn't know what they were doing. That's the reason for the scale. But yes.
Can you remind me one more time which test got scaled?
For the record, I don't know. It's the one that had the lower average. And if my friend was here, she could. Well, not you. Where's? She's not here either. This is the one that.
It was test A.
On ferrite, huh?
It was test A.
What?
It was test A.
Test A. Whoever asked, I'm just telling you because I don't remember.
You had B?
The graders are the ones that
I was gonna say
basically
A,
have
B, A, B, A.
All right. Now, back to operational amplifiers, and this I gotta tell you is, it's easy, but it can drive you bananas. I'm gonna give you a bunch of homework problems on this. And operational amplifiers, I gotta tell you, is the one thing that if you look around on the internet and other places, you're gonna see a lot of canned formulas that'll get you in trouble. If you start trying to memorize just canned formulas, it'll get you in trouble. Remember what I told you, with operational amplifiers, there's one thing that's critical, these are op amps. That's the symbol for an op amp. You can forget about anything else. It's a triangle. It has two differential inputs. This is the minus or inverting, this is the plus. It's called a non-inverting terminal. If you're doing laboratory work with op amps and it's low frequency, everything I show you here is valid. If it's higher frequency, and if there's an exactness to it where you need precision, like 3-4 digit precision, then there is a trickle current you have to worry about. But for almost everything, what I'm showing you, this method works. This is an ideal op amp, and I can put the words ideal here. So this is the perfect world. This is the output terminal. The general rule is, this is V minus and this is V plus. These are the inputs, they're differential. V minus is equal to V plus. That's the basic truth. Whatever the voltage is on one, it's the voltage on the other input. The second law for operational amplifiers is no current goes into them. So I minus is equal to 0 and I plus equals 0. Which is counterintuitive. Your first thought should be, well, Dr. Baginski, I can put 3 volts there, and so I put a voltage there. And the minute that happens, the operational amplifier does not work as an operational amplifier. Then it goes into what's called the saturation mode. You don't have to worry about this. However, under normal operation, the voltage there is about 0, and the current going into them about 0, almost perfectly 0 spec. So how do they actually create that type of environment? Well, the operational amplifier represents thousands, maybe tens of thousands or more of transistors that are put together in what's called a differential pair and other modes where they can make this occur. They make it occur electronically. Right? If I had time, I would take you through all this stuff. We're going to go through some basic circuits but later on, but not yet. So now, what actually happens? What's a typical circuit? When there's supply voltages out here, there's plus VCC, you'll see in some problems minus VCC. They're just saying there's external supplies that are involved. It's not just a triangle that does magic. So what's some typical circuits? Last time I did the standard inverting amplifier. That's the minus, that's the plus terminal, and I grounded the plus terminal. Then I put a resistor here, just R for starters. And then I put a voltage here, which would be your input voltage, Vs. Then I put a resistor here, call that R1, call that R2. And I took the output right there, V out, with respect to ground there. Now this is the most common operational amplifier circuit you're going to see. This is just a general circuit where you can increase the magnitude of the output voltage by the ratio of R2 to R1. Now when you do this, do it the way I told you to. I said there is no voltage across them, right? So what you do when you solve these things, try to find the voltage on one of the input terminals. How many see that this is 0 volts here? We went through it last time. Clear? I'm going to go through it a little quicker. Are you with me? 0 volts there, 0 volts here. What's the voltage here? 0 as well. That's 0 volts. You see we have a voltage across R1 of V1. It's plus V1 and 0. Does everybody see that? You work with me on this, you won't mess up. If that's the case, then I have this current. I have I1. I1 here would be equal to V source over R1. That's the key. Are you with me?
What's the top resistance?
Say again?
The R and R2.
This is just R1, this is R2. Okay? They're just labeled.
Yeah, that's good.
Now, if I have that, this is key. The amount of current going into this negative terminal is, say it with me, 0, correct? You get used to this saying this, you're not going to mess this up. Nothing goes in there. When that current I1 has to go somewhere, and it goes here. We're going to do it like this time. Again, because I didn't give, the homework didn't post, so I got to make sure everybody sees. With me? Now, if that current goes that way, then what is the voltage drop across R2, plus to minus? Just say. It's just I1 times R2, right? So the voltage drop here, and I'm going to call it V2, is just I2 R2. Agreed? It's the current going into it times R2. Agreed, everyone? Or I1, pardon. It is actually flowing through I2, but it's the same thing as I1. I1 times that. Agreed, class? I should just probably put I there. Now, I know what I is. It's Vs over R1. So that means V2 here, put it here, V2 is actually equal to Vs times R2 over R1. That's the magnitude of the voltage across R2. And this is the part people mess up occasionally. But I don't care about that. I care about this voltage, right? Now, normally, and I want to say this one time, normally what you would do if you were doing this would sum the voltages around a closed loop and it would be 0, correct? And it doesn't matter if you go clockwise or counterclockwise. So work with me on this one just for the record, so next time I say start from the negative terminal, everybody will understand why. If I start here, and I'm going to go all the way around this closed loop, sum voltages, you see you get an increase of V0 here. Everybody? I've got V0. Now when I go from here to here, what do I get? A decrease, correct? What I've got there is a plus to minus, it's an increase of V2, correct, class? Y'all see this? That's positive, that's negative, this is an increase from here to here, it's V2, and it's equal to plus Vs times R2 over R1, right? Now, when I go from here to here, it's 0 volts, right? And I'm back to ground, and then I'm back to the point I started. So all this sums to 0. Are you with me? I'm just doing it one time to make I get a lot of strange looks and some strange questions about why do you start in the negative terminal and just go around to the positive. You're going to see it's the same thing as what I'm about to do. Do you all agree that's right? Fundamentally right. So there's no issue with what I did. I just summed the voltages around a closed loop, set them equal to 0. Now, if I take V out to the other side, it becomes minus V out. It's as simple as it looks, right? And then I can multiply both sides by a minus, and I get this. And V out would be minus Vs R2 over R1. What that means is the output is inverted. If the input is a positive signal, the output is negative. But it's also, its magnitude is dependent on the ratio of R2 to R1. So if you wanted, and remember this is going to be an AC signal generally, if you wanted a large voltage amplification, you would want the ratio of R2 to R1 to be large. Now, the actual thing they usually want is the voltage amplification factor, which is V out over V in, or V source. And that, in this case, is simply minus R2 over R1. And that is the voltage amplification for that circuit. Now you can put values in anything you want. Suppose R2 is 100 k ohms and R1 is 1 k ohm. You would amplify by a factor of 100 in terms of the magnitude. Does everybody see that? This is typical. Now, if you wanted, and I'm going to add it right here. So remember, it's just the ratio of those two resistors, but always make sure you can go through it from the beginning. Because just remembering what circuit topologies look like will get you in trouble. Is everybody good with this? Now the next step. So some of you will say, but I don't like that negative sign. How do I make sure the output is actually going to be positive, the input times the scale factor? Well, there's a couple things you can do. We can actually do this. We can just take this and have another resistor. And the resistor you can just label as R. Have it go into the negative terminal. Ground that one. Have this as R. And now your V out over Vs will be equal to just R2 over R1. What this does, if this equals this, right? Then if you just cut it right there, say that's a source, there's a voltage there, correct, class? Well, whatever that voltage is, the output is going to be minus 1 times that voltage. Do you follow me? Can you all see this back there, guys? And that means this will be positive. This thing I just drew here, That's called an inverter. It takes whatever the value of the voltage is coming in, and it makes it negative that. So if it's 5 volts coming in, it's minus 5 volts coming out. And it just inverts it. Everybody got that? Now I'm just showing you some of the standard stuff. I'm going to go through another one, and this one's going to force you to think, because you're going to have to reason your way through a lot of these at first. Once you do a lot, then it'll be second nature. And I'll give you problems with actual values too. They're still ideal. If you work with these, you'll notice that a lot of times there's capacitors and resistors involved. I will do that later. That's if you want filtering action, if you want to make, or you want an integrator or a differentiator, and I'll get to that in a second. But first I've got to go through the basic circuitry. Now here's another one I want you to work through with me. You tell me what it is. Suppose I have this. Put a negative, positive here. All right. There's my output. And now I'm going to have this. R1 here. R2 here. And I'm going to put this to ground. And then I'm going to put a value of plus to minus Vs here. Right, and I'm going to ground this. We use grounds a lot. Instead of running wires all over the place, the ground symbol means 0 volts. We always use them. You're going to see that a lot. And mechanical engineers will see this a lot if you're working with electric motors to drive something. And probably aerospace engineers too. Now that all this UAV stuff is up and running like crazy, you'll probably run into a lot of that with as far as actuators and things like this. How many are aerospace in here? All right, how many are mechanical? Wow. About everybody in here is going to run into this. You're going to use it. All right, if I look at this right here, how do I get the output voltage? Remember, Vs is what's known. We could put hard numbers in, but it's better to probably work in just symbolism at this point. So if that's Vs, that's on this terminal, right? The negative terminal? What's the voltage on the positive terminal? Class? No, not negative Vs, just Vs, right? Whatever the voltage is here, it's here. If it's 1 volt here, it's 1 volt here. 10 volts here, 10 volts there. Got it, class? Always the same. There's no voltage difference. I'm glad you said that. So this is Vs, right? Now, if you have Vs, don't you have Vs here as well, right here? Class? Please work with me. Are you with me? If there's Vs there, don't you have the current through this resistor right here? Isn't that current right there, I1, equal to just Vs over R1? Please take a look. Think about it. We're reasoning it out based on the laws. No voltage across, no current into. Remember, there's no current into or out of that positive terminal. Got me on this, class? Can everybody see this? All right. Well, if that current is flowing here, where does it come from? And this should bother you. It's coming from there, right? But it's coming out of nowhere. It's coming out of V out. Well, that's because this chip right here has got a plus to minus power supply. And now the current has to come out of here. And that is going to be your I1 flowing there. It's the same thing as this. Do you all see this? Can you all see this, class? How many see this? All right. All right, you're shaking your head. I appreciate honesty. Answer me this question. Do you understand the voltage here is the voltage here? And that voltage is Vs. Do you see that? If that voltage is Vs, it's Vs there, isn't it? Isn't Vs to 0 the voltage across R1? So wouldn't the current through there be just Vs over R1 flowing down? Now how much current can flow out of that terminal? Class? 0. No current can flow out of the positive terminal. You hear me on that one? Where does the current have to come from? From over there. And so that current I1 is the current flowing here. Can you see it? Just take a moment and think. Yeah?
So why does V not affect the voltage of that node?
You don't know what the value of V0 is, right?
No, we don't. But
V0's being controlled by the ratio of those resistors. Remember, the value isn't set in stone what's set in stone is the ratio of these resistors, and that the current here is now set in stone, then that current's set in stone, which fixes that voltage.
Okay.
All right, that's the way it goes. Now, here we have I1, so then what's the voltage across R2 right here? Well, do you agree it's just I1 R2? Right? And I1 is just VS R1. So V2 is I1 R2, which is equal to VS times R2 over R1, correct? Now, work with me here. Do you all see what I'm doing? It's just deductive reasoning. There's nothing that is not seen based on the fundamental laws that say no voltage across the input, no current into the input. Got me? Take a good look. At least it should bother some of you. That doesn't seem fair. It doesn't matter if it seems fair, it works. Now if I come over here, what is my V out? Now please watch. Now I say, well, V out, I start at the negative terminal right here, right? That's 0, correct, class? Can you all see this? I come around here, that's 0, right? I go up, I get an increase of VS, don't I? You all see this? So I get VS, and then I get an increase of VS times R1 over R2, correct? From here to here, that would be VS R1 over, or R2 over R1. Correct, class? How many see this? So this is going to be VS plus VS times R2 over R1, or it's VS times 1 plus R2 over R1, and that's the output voltage. You'll notice one thing about it didn't invert, did it? There's no inversion, is there, class? It's positive, is what I'm saying. Y'all see it? There are other reasons why you don't do it this way. Almost always we use these as inverting amplifiers. It has to do with stability reasons and other things I can't get into. But when I have this, then what is AV? What is the voltage gain? V out over VS is equal to 1 plus R2 over R1. You all see that? Here, you'll notice that the voltage was not at the positive terminal, but the negative terminal, the input voltage, right? Yet it caused a positive output. Do you all see this? Yes, sir.
That equation, can you go over the path that you took?
Sure. All right, this is my V out, correct? I'm going to start at the negative terminal. You give me, if I start at the negative terminal and work back to the positive, all the voltage drops or increases are going to be equal to V out, right? If I start here, that brings me to this point. They're both 0. Then I go from here to here, it's VS, right? From there to there, it necessarily, right? It's VS. Then from here to here, it's going to be what? The voltage across here. Well, what's that voltage? It's that current, I1 VS over R1 times that resistance, R2. Or it's VS R2 over R1, or it's this. Right? And that's how I got it. How many see this right here? Do you not see it for real? Don't you guys see it? Or, I mean, are you not raising your hand just out of spite? Or, I mean, how many see it? Just tell me so I can move on. I've got to make sure. If you understand this, if I'm boring you, fine. I prefer you be bored because you see it. But I got to know if you see it or not. Now, the next thing I'm going to do, this is a non-inverting, simplest kind of op-amp, all right? Here the output wasn't inverted. Most of the time you want them inverting for stability. Remember that in your circuitry and laboratories. How many have used op-amps before again? Was it for measurement circuits? Or when you did it was always inverting, wasn't it? Do you remember? Almost always use inverting. Almost always. When I was where you were, the operational amplifier that I used was a 741. I don't even know if it's still made anymore, but it was the old standby. Cheap as they come, and it did everything you wanted up to about a couple hundred thousand hertz. You know, it was dirt cheap till you could blow them up. Who cares? Get another one. It didn't matter. Nowadays, there's some really expensive circuits out there you got to be careful with, and they're usually paired with things that are like microcontrollers and stuff like this. You get a chip that's got 2 or 3 amplifiers. It's got a microcontroller, and you blow one of those, now you're out a couple $100, sometimes more. Has anybody worked with chips with microcontrollers in here? You know what PIC is? Or microprocessors? Nothing? Okay. Well, you're probably going to use them, especially MEs. You're probably going to use a lot of stuff with microcontrollers, but I don't know where you get that in your laboratory. All right, next circuit. So far we've got those two bases. Well, so far I showed you how to amplify a signal, right? Ratio of resistances. Cause, you can get an amplification. Do you all agree with that? That's most basic use of an op amp. All right, now you can also use an operational amplifier to sum, or really to sum voltages if you wanted an adder, an analog adder. Watch this. So now I'm going to take my basic operational amplifier and I'm going to split it negative, positive. I'm going to ground the positive lead. Now what I'm going to do is put a resistor here, R, and I'm going to go ahead and I'm going to say this is going to be V1, pardon me, resistor here, and that's R, just R on that. Then this is going to be an R, this will be V2. This is going to be an R here, and this is V3. All these voltages, if you ever see a drawing like this and you just see V1 hanging out of here, the other side is to ground. They assume it's to ground and they won't even show it. Follow me, class? So V1 goes to ground, V2 goes to ground, I mean the other side of it, V3, the input, the other side of the input goes to ground. So it is a differential drive, all right? And it's grounded there. Now, as a matter of fact, let me do it this way. Let me even get rid of this resistor, make it even easier. I should do it this way, just like this. So it's as simple as possible. Now, watch and you'll see. I claim this is going to add them up. It's actually going to add them up and invert them, but I'll show you why. Please watch. What's the voltage here? 0 volts, right? What's the voltage here?
0.
You agree with that, everyone? All right, what's the current here? If that's 0, it's 0 here, right? That's V1. What's the current here? It's I1 here, or really, yeah, call it I1. It's just V1 over R, right? Do you agree with that? Right? How many see this? It's very simple, right? Find the voltage difference, divide by the resistance, you have the current. Can you all see this? What's the current here? V2 over R, isn't it, class? Right? You with me? What's the current here? V3 over R. Absolutely. It bothers you. Something doesn't seem right. How can that be? Well, the other side of all those resistors are theoretically at ground, aren't they? You only are driving them at one end and the other side's ground. Now, what current do you have? Well, you've got all that current flowing this way, right? You've got V1 over R, V2 over R, V3 over R, don't you, class? And you can make this R1, R2, R3 if you wanted that. You want that flexibility, but for now I just let them all R. All that current flows here. Can it go into there? No, and I make sure I'm going to underscore this over and over again until you be irritated with me, because I want to make sure you don't make that mistake. I'll see people do this on tests. So it must go this way, right? You all agree? Remember, it can't flow into it, and it's flowing somewhere. So it's got to go around to V out, right? It's got to go that way. And V out's to ground, by the way. And you're right if you're thinking, well, why isn't there a resistor there? There could be, it will not change this. You understand that? It will not change what happens. Now, if that's going this way, then what is the voltage across here? Well, that voltage across there would be the net current in that resistor times the resistor, right? You agree with me? So what's the net current going into there? I call this just VR right here. VR would be equal to the current going into there, V1 over R, plus V2 over R, plus V3. All of these are divided by R, and then it's times R. Or VR is equal to V1 plus V2 plus V3. Can you all see that? That's the voltage across this resistor, right? In the back, guys, you with me? I'm trying to make this as easy as possible, but you do have to be attentive. If you're playing on your phone or something, you're probably going to lose it. You're not going to have this. So what's my output going to be? Think about this. I start here, right? I go to here, it's still 0. From here to here, it's 0, correct? And then from here to here, it's a what? Decrease of V, that voltage across that resistor, or it's minus that. So V out is equal to minus the quantity V1 plus V2 plus V3. And you can add as many as you want. All right? Furthermore, if you wanted to scale these things, or if you wanted to weigh one twice as much as the other, then you can make the resistor 1/2 the value. You can do all sorts of stuff. Some of you are saying looks like the beginnings of analog computations. In fact, this is an analog computer's basis. This is the beginning of adders. You are too young to know what I'm talking about, but when I went to college, we built, quote, analog computers. We solved differential equations, anything we wanted to do. What we did is we take just plain old jumper cables and plug in things. We had operational amplifiers. We connect them up like this so we could sum. You're going to see we can solve differential equations, we can add up things, we can do any mathematical operation with operational amplifiers we want, and in real time. And that's the reason they can be used for things like control systems. Y'all had systems here, right? And control systems, well, you can do it in the analog domain. The bad thing about analog is it's very expensive in terms of the amount of resources you're using for it. And it's also slow. Nowadays, everything's high-speed digital processing. Have you guys had a digital processing course, digital signal processing or digital image processing yet? I recommend you take it, especially the MEs, all right? Because all the stuff you're going to be doing is in the digital domain. It's very fast, it's sampled. You had signals and systems, right? A course in that? Sampling, you've had sampling theory? Come on, you have.
The
What
Nyquist?
are you, Emmy?
I'm Harold. We had a lab about it, about like Nyquist sampling theorem.
Yep,
but it had
that's right.
systems
How many
class.
know Nyquist sampling? Really, a lot of MEs don't. I'm a little concerned. How many are scheduled to graduate? Have you all heard it? You guys, you're Arrow back there, right? You haven't had it? Oh my God. It's happened to my college. All right, getting back to this, you all see how this works? Now, if you wanted to make it positive, just put an inverter stage, right? You could do it that way. But that's, yes?
So you were summing the voltage drops from the minus part of the amplifier, right?
I just am finding V out. Now that's positive, that's minus. Normally, I could go around and say it's an increase of V naught, then I could be an increase of VR equals 0, right? And I take VR into the other side and make it minus VR is V naught. All right, so it doesn't matter how you do this, as long as you understand it. And if you have any questions, see. Are you guys good on this so far? Now, bear with me. Next, so far I've done addition. Y'all see that if I wanted to do anything else with this, this is addition. I could probably do subtraction. I'm going to show you how to do a whole bunch of stuff next. But first, the next logical thing to do is show you how to do an integrator and differentiator, because that's always something that pops up in your work. You're always going to take a derivative or an interval of something. And this is with analog components. This is still used today for controlling things, but for the almost all digital signal processing now is done in the digital world. It's sampled and then it's done digitally. All right, now the next one is going to be something, and this is called an integrator. All right, I take my standard differential or operational amplifier, and I put a resistor here, and here's my voltage, plus the minus Vs here. I'm going to ground this terminal, and then I'm going to put a capacitor here. And this is going to be V out to ground. Now I'm putting this as a function of T for a reason, because I use the word integrator. You don't have to do it this way, but this, hey, I don't need you today, it's okay, go ahead, I'm sorry. I thought you were talking. If I take a look at this, right here, I notice that this is 0 volts. Do you all agree with that? Class? Right? Ground, 0 volts. Ground is just those dashed lines. How many have seen ground symbol before this class? I was hoping everybody did, because in physics laboratories, they used to teach this all the time. They taught you that before you built anything. The other thing they taught you in physics lab was that black was ground and red was hot, because it was always DC. Do y'all remember that? How many know that for DC stuff, black cord ground, red cord hot? For cars, it's 12 volts. Now, how many know for a house wiring, black is hot? All right, there's something you take to the bank. That is not ground in that wall. If it's an AC application, black is hot. Remember, it'll save your life. Because the natural instinct is to think it's ground, and it isn't. And you'll kill yourself if you don't know what you're doing. I'm telling you the truth. What? Did you have a question? You asked the wrong guy that. I mean, I think it was some kind of Nazi plot with this color code. You don't know how many people did dumb things because, I'm not kidding about this. I don't know. It's the stupidest thing in my life. Why can't you just be consistent for
Wait,
once?
not kidding. about
Just
what?
once, these electrical codes have to be crazy to begin with. You gotta see the American wire gauge, the stuff that they do. You know what gauge is?
Yeah.
You know where it comes from? It's how many balls you can put in a ring. It's like the stupidest possible thing. Instead of having a diameter or something like that, it's gauge. 12 gauge shotgun should be bigger than a 10 gauge.
How many balls make up 1 pound of lead?
It is, well, I'm not gonna. I have problems with a lot of stuff the English have done over the years. That's one. All right, back to this thing, guys. Follow me. What's the current here? Just take one look. What is that current? I'll call it IR.
VS over R.
IR is simply equal to VS of T divided by R, right? Y'all agree with that?
Yeah.
All right, now where's that current going? How much goes into the negative terminal?
None.
None of it. All goes around here. Now, on a capacitor, you don't see this all the time, so you can be a little rusty. If you have a capacitor, a value C, and you have a current flowing into the capacitor, C times the differential of the voltage with respect to time is equal to I of T, which means this is the voltage V across the capacitor. Now, it's important you see what I'm about to do. This is a differential equation. If you wanted what the voltage was, I would have to take 1 over C and integrate, right? Integrate I of T dt, and it would be from, really practically speaking, 0, but technically minus infinity to T, and that would be my V of T. You'll notice the only thing I've done is divide by C, and then integrate both sides, so I get, instead of a differential V, I get V of T. Agreed, class? All right. So that means this voltage that I labeled here, what I'll call VC of T, is equal to 1 over C times the integral of I. In the integral of I there, I is Vs over R, so I'm going to put the RC out in front, right there. And it's the integral of Vs of T dt, technically from minus infinity to T, and technically I'm supposed to prime those. And that would be Vc of T. Can everybody see what I've done there, class? I've simply gone ahead and said I know the current into the capacitor, therefore I can find the voltage by integrating that current and dividing by RC. All right, now what's the output voltage going to be? Well, this is the same as before. If we start here, we can see we have 0 here, and then it's going to be minus that voltage. Y'all with me? Instead of an increase, it's a decrease. So that's minus the voltage across the capacitor, or it's minus 1 over RC, the integral of Vs of T dt from minus infinity to T. You can find that. One thing you can see here too, let me just be frank about this. One thing you can see is that still is inverted, right? But that doesn't bother anybody in the real world because you just put the next stage is that it's going to be an inverter, you got a positive value, right? So that's not a big deal at all. But now I can basically get the integral of an input voltage, which is very important. That's called an integrator. The next logical thing, I showed you a summer. I can show you a difference too. It's even easier. The only thing I'm going to do now is show you that's an integrator, a differentiator. Should make sense. Can you all see how that's an integrator right there, class? Everybody? based on this, right? One last thing I'm going to say with operational amplifier circuits, with very, very few exceptions, you don't use inductors. Almost no inductors ever, because first, inductors they're bulky and they have a field around them that will cause electromagnetic interference to nearby components. So in general, we don't try to ever use an inductor in these circuits unless it's absolutely necessary, and that would be for something like really a tank circuit where you have a resonant effect, but I'll get to that later. Next, we do a differentiator. Some of you will be doing, don't you all have senior design in ME&E? Right? Is there anybody in senior design right now? 1, 2? Well, usually senior design has something where you build a circuit component, either a measuring device or an actuator, something like this, and it will use operational amplifiers almost always. How many have used op amps before in here? Wow, that's very low. I'm kind of surprised. Really, for laboratory work especially. All right. Now, next, this is called a differentiator. And if this is your standard operational amplifier, now we put a capacitor here instead of on the output term, from the output terminal to the input inverter. All right. And here, well, you can see really what I need to do is start here, that's 0 volts. 0 volts is there, means 0 volts is there. That's the key point. Now, do you all see I have a voltage across that capacitor of Vs? Can you all see that? So if I have a voltage of, first I gotta make sure everybody sees this. If I look at this, the negative terminal's here, that's 0, that's 0. Vs is on the other side. I got Vs across that capacitor. Do you agree? So now I have a capacitor that has plus to minus Vs of t, which means that the current I of t flowing into it is C times dVs of t dt. Do you all agree with that, class? C times dV dt, right, is equal to I of t. Everybody got that? So that means this current here is now, I can call it IC of t. IC of t is just equal to C times dVs of t dt. Agreed? By this time, a lot of you see the end result already. This is V out, right here, with respect to ground. All right? Well, I keep forcing this on you, I know. That current's flowing here. How much of that current goes into the negative terminal? 0. It all goes this way, which means I develop a voltage there equal to R times this current or times this, correct? You agree with me? So this voltage is just R times C times dVs of t dt, and that's plus to minus. I'll let you catch up. Just so you see the steps. Remember, it's all based on a knowledge of what the differential equation is that governs current and voltage in a capacitor, and then going through the analysis, because there's no voltage across the inputs, no current into the inputs. Now I find out my V out. How many can see this now? It's just going to be minus that voltage by now. How many can see that? Okay, good. And it's exactly it. That output voltage is going to be minus R times C times dVs of t dt. And now you can see I'm taking the derivative of the input signal with respect to time. The RC is a scale factor. It depends how large you want it or how small you want it. That's R times C. Pick your value and set it. Minus sign means it's inverting. If you wanted non-inverting, you would put another operational amplifier where 2 R's between the input and then between the negative terminal and the output of the same value. Yeah.
If you were in a situation where you're like doing this problem and you were rushing or something like that, and when you use something you went the wrong way, so you end up with a positive output instead of a negative, is this is this pretty much always negative, and then you use
Well,
the
most-
inverter to change the sign?
Listen, I'm just gonna tell you, most of the time in the real world, for real problems, it's inverting for stability reasons, among other things that I can't get into because it has to do with the internal workings of the operational rectifier. When you get problems, you will get a positive output, but in the real world, most of the stuff has a negative output. You won't mess that up if you do some problems. I'll give you a bunch to, make sure they post it, no matter what. All right, any other questions? All right, on Monday, I'm going to give you a quiz related to OpEx, all right? Basic operational exercise, not advanced, basic. Got me? Okay. See you then. Have a great one. I've got a question for you. Anybody going to the Alabama LSU